Greetings of the day, dear students. Welcome to Basic Electrical and Electronics Engineering class. In this video, we are going to discuss about the losses in transformer. What are the different losses we are having, and iron or core losses, copper losses, and again this iron and core loss gets subdivided into hysteresis loss and eddy current loss. All those things we will see and their formulas, and also we will discuss one small example on this topic, right? Yeah. Now coming to the losses in the transformer, as it is a static machine which is not having any rotating parts, there won't be any friction or windage losses. If you come across DC machines like DC motor or DC generator and AC machines, as there will be some rotating parts, while considering their losses, there will be friction and windage losses. But with respect to the transformer, what happens is, as there are no rotating parts, we won't have any friction or windage losses. And now it is divided into iron or core losses, and the other one is copper losses. And this iron or core losses will be constant, and these copper losses will be variable in nature. And these copper losses are mainly due to the resistance of the winding. Okay, and the winding will have some resistance, and because of the current flowing through the winding, some I square R amount of losses will be there. With respect to this iron or core losses, as the winding is wound, primary winding on secondary winding on some core, right? They will have some hysteresis loss and eddy current loss. Now, this hysteresis loss is mainly due to the alternating flux in the core. How do you understand that? The flux phi is alternating in nature, is sinusoidal in nature, and this flux tends to change from time to time. Due to this alternating flux in the core, it gives rise to some amount of losses will occur, and these losses will appear in the form of heat. These losses are going to appear in the form of heat, and in such kind of electromagnetic equipment, these core losses, they will play a very important role in determining the rating of the equipment, and also the efficiency and the temperature rise. All this depends upon these losses. All these things will depend upon these losses. So iron or core losses are mainly due to the alternating flux in the core. This point is important. Alternating flux in the core. Now, if it is hysteresis loss, what happens is, this is due to the variation of the flux density when it is plotted against the magnetizing force H, right? For one cycle of excitation, it will be in the form of a hysteresis loop. It is something like so what happens is, if you plot a graph between the B, flux density, and magnetizing force, you are going to get a shape like this. This loop is called a hysteresis loop, right? So for example, if the value is slowly increased and it takes one path, for example CBA. Now if the value is reduced slowly and brought back to its original value, then it won't follow the path ABC. Instead of following ABC, what happens is, it may follow A, F, E and D. So even though it is something like 0 to 1, 1 to 2, 2 to 3, you are going slowly increasing the force, and you may get a shape CBA. Now it does not mean that slowly if you reduce the force, it will follow back the same path. Instead of following the same path back, okay, it will take some other path. If you join all those points, you will get a shape like this. This is called hysteresis loop. So here this variation of the flux density Now this loss, hysteresis loss, is given by the formula pH equal to KH VF BM power 1.6. Very, very important. Number of times this formula will be asked in objective exams also. In objective exams, if you observe, it is directly proportional to the frequency and BM power 1.6. BM power 1.6. In this formula, this KH represents a constant value and which depends upon the material of the core, and V indicates the volume of magnetic core. F indicates the frequency of the alternating magnetization in H. F indicates the frequency of alternating magnetization in H, and Bm indicates the maximum flux density expressed in Weber per meter square. Bm indicates the maximum flux density. So this formula is very important, dear students. The hysteresis loss pH equal to KH VF BM power 1.6 and the units are watt. WATT watt. Right? Now, how can we minimize this hysteresis loss? This point also very important. They will ask what are the different methods to minimize the hysteresis loss. It can be minimized by using some materials like nickel iron alloys or silicon steel. By using this silicon steel material or nickel iron alloys, so that they will have very small area under BH curve. Right? So because of that, the losses will be less. The losses will be less. If you are going to use nickel iron alloys or silicon steel, the hysteresis loss can be minimized. The hysteresis loss can be minimized. Right? Now, what about eddy current loss? These eddy current losses are due to the circulating currents in the closed path. For example, number of times we are saying primary winding and secondary winding. Now these windings are wound on a material or core. On the core, these windings will be wound. It will have primary winding, and it will on that winding, on that core, these windings will be wound. Right? Now, some amount of flux will also be linking these ferromagnetic materials body. The body of the core will also be cut by the flux. Now, because of that, some currents will be established. Those currents are called eddy current losses. Those currents are called eddy currents. Now, how can we minimize that eddy current? For example, instead of using a solid thick block of core, if you cut that core into small laminations, if it is laminated, what happens is, it's for example, observe here, R equal to rho L by A. Our target is this eddy current losses is to be minimized. If the current to be low, R must be high. If the resistance is to be made high, right? Now this area of cross section is to be minimized. Now this effective area of cross section can be minimized by laminating the core. What happens is, instead of using a single thick block, okay, the laminated sheets having very small thickness, and this will increase the resistance of the core. Once the resistance is increased, now this eddy currents, the path for the eddy current, okay, is opposed by the high resistance. Now those currents can be minimized. Eddy current can be minimized by using what? By using the laminated sheets of the core. Instead of using a solid thick block, you better use a laminated sheets having small thickness. Because of this, what happens? Resistance will be increased so that the current can be reduced. Right? Now, the eddy current loss is given by the formula PE equal to KEVF square BM square T square. Very, very important. Dear students, at this level, no need of derivation of how to derive this hysteresis loss formula. and eddy current loss formula. Derivations he will not ask you in the examination, right? We are supposed to do the problem. What is the hysteresis loss formula and eddy current loss formula? That is important. In this video we are not discussing about the its derivation, right? Yeah. Now this constant Ke indicates the constant of the core material, and V indicates the volume of a magnetic core in meter cube. F indicates the frequency of alternating magnetization in H, and Bm indicates the maximum value of flux density in Weber per meter square. T indicates the thickness of the lamination in meter. T indicates thickness of lamination in meter. These terminology are important, dear students, right? So two important key points. How hysteresis loss can be minimized? By using nickel iron alloys and by using silicon steel. How eddy current losses can be minimized? By using laminated sheets having small thickness. We can minimize the eddy current loss. So once the losses are minimized, okay, for example, some input power is given, so here there are some losses, and power input minus losses, that one only will be available as output. For example, if you are giving 100 as an input, if the losses are 20, only 80 watts will be available. If the losses are 40, 100 minus 40, only 60 will be available. If you calculate the efficiency, eta equal to output power by input power, if the output is less, the efficiency will be less. So by minimizing the losses, the efficiency of the transformer can be improved. The efficiency of the transformer can be improved. Very, very low the losses, very, very high the efficiency. Like this, there is a need to minimize the losses. And as it is a static device, I repeat again, there won't be any friction or windage losses. There won't be any friction or windage losses. Clear? Now, and eddy current loss is proportional to the square of the frequency. Observe here, square term is there. For frequency you are having power 2. For flux density also we are having power 2. That is important. Directly proportional to the square of the frequency and square of the maximum flux density. If it is eddy current loss. If it is hysteresis loss, proportional to F Bm power 1.6. Directly proportional to F Bm power 1.6. If it is eddy current loss, directly proportional to F square Bm square, square of the maximum flux density, right? Now along with this, these two losses together, we are calling it as iron loss or core loss. Along with this, copper losses also will be there. This is due to the winding resistance of the transformer. Now we are having both the windings, primary winding and secondary winding. So in both the cases we will have the loss. The loss in primary side, I1 square R1. I1 is the current drawn from the primary side, and R1 resistance in the primary side, I2 square and R2. If you observe equivalent circuit transformation, this entire resistance simply we can refer with respect to the primary side. For example, if you are having a transformer, R1 side is there and you are having a winding primary side, and you are having secondary side resistance. This is primary side resistance R1 and this is secondary side resistance R2. Instead of separating these two, you can transform the secondary resistance towards the primary. For example, R1 will be as it is, and R2 will be there, and this, when this transformer secondary resistance is brought towards the primary side, right, and the indication you should give it as R2 dash. It is called R2 dash, and the primary side resistance will be same, R1 only. This is I1. Now this is I1, and here you are having V1, and this is the induced EMF E1, and this is the current, sorry, I2, right? Now this R1 plus R2 dash together we will call it as R01. Now while transferring the secondary side resistor or resistance towards the primary, your new value, it does not mean that here if it is 100 ohms, while bringing it towards the primary side, same 100 you should not take. That is a common mistake. We should not do that. Now while the secondary side resistor is brought towards the primary, its value will now become its old value. Old value is R2 divided by K square. Very important. Very important. Now this R1 and R2 together we will call it as equivalent resistance referred to primary. That is what we have written here. Very important, dear students. I1 square R01. R01 means it is primary resistance R1 plus R2 dash. Secondary resistance referred to primary. Secondary resistance referred to primary. Now your new value R2 dash value is given by R2 old value divided by K square. Similarly, if you want, you can bring this R1 towards the primary secondary side also. Then your diagram will look like this. This primary side is same like this. Now you have shifted. R2 is same, but you have shifted. You have brought the primary resistor, primary side resistance towards the secondary. Then the name you should give is R1 dash. It is to be understood as primary side resistance referred to secondary. Now your new value, this R1 dash will be equal to its old value R1 into K square. Very important. R1 into K square. In equivalent circuit representation, before watching this video, if you have completed equivalent circuit representation of the transformer, there we have discussed all these derivations and this representation, how to transfer from primary to secondary and secondary to primary. Clear? So dear students, what I want to say is copper losses I1 square R1 plus I2 square R2 over R I1 square R01. Don't get confused with this word R01. R01 simply indicates effective or equivalent resistance referred to primary. Now it is equal to R1 plus R2 dash. R2 dash equal to R2 by K square. Clear? Good. Now OR, if you want to write or express in terms of secondary side current, then I2 square R02. R02 effective or equivalent resistance referred to secondary, its value equal to R2 plus R1 dash. It equal to R2 plus R1 K square. R2 plus R1 K square. So these are all the important formulas with respect to the copper loss, eddy current loss and hysteresis loss. If you once look at this table, this if a question is asked, write a short note on about the losses of the transformer. If you draw this table, it gives good impression. The entire key points, this formula should be visible, and you make it in the box. This formula you please highlight, and you expand the variables, and you tell how the loss can be minimized. Then slowly discuss about the eddy current loss. Write the formulas, and then please tell how it can be minimized by using the laminated sheets, and then discuss about the copper loss. Write all these three formulas. Then it will help you to score more marks. Clear? Good. While discussing the DC machines, motors and generators and alternating machines, we will discuss about two more losses called windage losses and friction losses. Right? Yeah. Now let me see a small problem. The flux in the magnetic core is alternating sinusoidally at a frequency of 600 Hz. The maximum flux density is 2 Tesla and eddy current loss is 15 watt. Find eddy current loss in the core if frequency is raised to 800 Hz. the maximum flux density reduced to 1.5 Tesla. Simply what he's saying is frequency is increased and flux density is reduced. Then what happens to the losses? What happens to the losses? Just now we have discussed from these two formulas, hysteresis and eddy current loss. Majorly they will depend upon the frequency and maximum flux density. Clear? Now eddy current loss directly proportional to what? Bm square f square. Bm square f square. Now in the first case 15, the loss is 15 watts. At that time the maximum flux density is 2. At that time the frequency is 600 Hz. This is Bm. And the first case eddy current loss in first scenario. Now in the second scenario we don't know the loss. It is a question mark. It is proportional to, this is the second Bm2. In the second scenario this is Bm1 and this is frequency 1. During second scenario the frequency is some f2. Now this We2 by 15 will be equal to 1.5 by 2 whole square into 800 by 600 square, and it is around 35 watt. It is around 35 watts. Clear? So dear students, in this topic formulas are important. Please practice the formulas. Please write all the formulas at one place, and definitely you can easily do the problems, and you can attempt this question and you can get the more marks. Okay, thank you.